elasticity. And I want to prove this is actually kind of a really neat result. Let R be a ring of integers. If you want to know the elasticity of the ring of integers, this is actually Davenport constant P over 2, and out with less than or equal to the order of G. We have the order of G 1 and 1. So this is a theorem. I think most of it was due to the name of Valenza. Actually, Valenza only got part of the. He only got like an inequality for this one, which was actually kind of sad because I think Valenza actually agreed to the hard part. Markevich did it, followed up and finished off the. It got the equality. So the elasticity of the ring of algebraic integers is compute the class group minus Davenport constant. Both of these you can compute, and then take the Davenport constant divided by 2. And this is just notice that this is bounded well by the order of the class group itself over 2. G is 3 over 1. Of course, this expression makes no sense if G is the identity group, right? Because elasticity of 1/2, and the minimal elasticity you never have is 1, and so it's 1 in the case G is 1. It's interesting, the paper that Valenza first did in this appeared in the Journal of Number Theory in 1990, and at the bottom, which I don't know what happened here. It's got to be demoralizing. At the bottom of the paper, if you look, it says received by the editors October 12th, 1980. So that's you always have to explain that also, that the refereeing process sometimes takes a while in mathematics. Although I don't know if we can blame the referee, or maybe the author moved or something like that. But anyway, 10 years has got to be close to somebody's record. So let's prove this. It's 10-year theorem. If G is trivial, then results. Because after all, this means that that you have in fact a UFD, and so the elasticity is in fact 1. In fact, the elasticity is also 1 in the HFD case as well. So let's suppose that the order of G is n bigger than 1. And just for notational purposes later, I'm gonna let R be the Davenport constant. Okay, so let's let it's on the class group. Let's let this class be 0. I want this to be a 0 sequence with no proper subsequence of maximal length. course, this is nice. Because of course, Davenport constants are, so this is the maximum length zero sequence I can have that has no proper subsequence. So, we notice that, of course, this is proved with negatives. Change the sign of this or take the classes of the inverses of this. This also gives a zero sequence with no proper zero subsequence. Now, what I'm going to do now is I'm going to start selecting ideals. Select PI class and let's see Q J class IJ inverse for the minus class of IJ. How would you like to say it? And note that by our selection here, notice that this is a the product of these is because the fact it's a zero sequence. The product of those prime ideals is a principal ideal, and more than that, it's irreducible because there's no proper prime subfactorization of alpha that's principal. So you can't break this down any further. By the same token, I have beta on that. Also, do this, I'm going to call PIQI, because of course, notice that PI is this and QI is in the inverse. This is also principal, so I'm going to call this gamma I. And I make the observation that alpha, beta, and each gamma I are irreducible. Because this is a zero sequence, no proper zero subsequence, and since these are non-principal and their product is principal, it's clear that there's no subsequence. This proper subsequence is zero. So we get an elemental factorization as follows. So if we compare these factorizations of ideals, we obtained well, multiplying this times this, I get alpha beta. But now, considering these paired off like this, I get gamma 1, gamma 2, gamma R. Now, these are the same as principal ideals, but let me do this element wise. Alpha beta is some unit times whatever it is. So what does this give me? this gives me notice that this factorization right here gives me at least R over two, right? Well, in fact, this one gives me R over two for this. So that means, of course, lurking in the ring somewhere, theoretically, there might be a factorization of bigger elasticity. So the rho of R is greater than or equal to R over two, which is Davenport constant over two. Everybody okay? So this gives me that the elasticity in this ring of algebraic integers is at least the Davenport constant of class groups divided by two. Now, I want to get the inequality in the other direction, which is actually one that's a little bit more involved. So I want to get it the other way. On the other hand, let us suppose that we have the irreducible factorization factorizations say alpha 1, alpha n is beta 1, beta n, like that. Let me also make another assumption. Okay, so why can we assume that none of them are prime?
If they're high on mountains.
Right, we could divide them out.
Increase the
That's
elasticity.
exactly right. Let's say that alpha 1 is prime. That means that one of these has to be prime over here. Let's say beta 1 is equal to alpha 1. So you cancel that out, now you get the shorter factorizations, which actually jacks up the elasticity, right? So what I want to do, let me invent this notation here. So each alpha I is equal to, so since none of these alpha i's, we're assuming none of them are prime, they have to be products of non-principal prime ideals. That's the only way if they're not principal primes themselves. So we will assume that each alpha I can factor into prime ideals as P I 1, 2, let's say P I T sub I. And so of course, the first subscript I refers to which irreducible I'm factoring, and this second subscript counts the length of this into prime ideals. I can bound that TI. How can I bound it? Right, because this is a zero sequence with no non-trivial or no proper subsequence that is a zero sequence, because this thing is irreducible, right? And the longest is the Davenport constant. Everybody okay with it? So we have the following ideal factorization. So forgive me for this. Yeah, this is kind of Yuck City, but we'll write it down. This is P1, P1, 2, P1, T1. So there's your out. 1, P2, 1, P2, 2, P2, T2. And finally, alpha N is PN1, PN2, PN T sub n. And there we go. Now, so that's one, yes.
Do we care that we can say TI is greater than or equal to 2, or? Is that matter?
Yeah, that's, it never hurts to make an observation, it's correct. Well, usually doesn't. And each TI is greater than or equal to, because of the fact that we're assuming that these are non-principal. So, now, I want to sniff around and try to find out other ways to factor this, right? Well, any other principal ideal factorization I get, any other element-wise factorizations, principal ideal factor, must involve exactly these primes, no more, no less, right? That's the magic of having every ideal factor uniquely into product of primes. So if I'm going to reshuffle this, so my question is how can I refactor? Exactly. Prime ideals above. So notice that in principal ideals, theta, yep. Notice the longest possible factorization so maximum or M. So how can you make this as long as possible? Occurs if you can pair off these primes, right? So any one of these are non-prime as well, right? So they have to consist of at least 2 non-principal prime ideals. Theoretically, each that I has prime factorization. Let me say prime ideal factorization. Only 2. So in other words, to make this as long as possible, what you'd have to do is use as few prime ideals for each of the betas as possible. So this means that M, so however long you can make this, is no more than T1 is T2 is Tn. So however I can rearrange this to make this betas, the number of betas to be no more than that. I mean, it's that or less. And so that comes from just dividing by n. And this is no more than, well, what are these t's, right? Well, these t's are all less than or equal to Davenport constant. So this is nr, because there's n of them, less than or equal to nr over 2n. So r over 2. And there you go. So let's finish the thought here. So rho r is now no more than Davenport constant g over 2. So there you go. And of course, so greater than or equal to dg, less than or equal to dg. So rho r is exactly. And we've already observed the Davenport constant of any group is less than or equal to the order of the group. And so there you have it. Okay. Any questions on that?
Do you happen to know if the original paper or the follow-up cited Carlet's result? You said that result had kind of flown under the radar at first.
Well, the original paper actually didn't come out until 1990. So I think that actually it did. I think actually the first citation of Carl's paper, which was written in 1960, I think was in 1976. And then there was one more in 1980. And there were like a small smattering of these. You know, there were very few references to it until 1990. And then, yeah, it took off quite a bit.
But you said it had been submitted in like 1980, so.
Yeah, but see, I suspect that with 10 years, somebody might have pointed out to the author that if they hadn't cited that paper, that they probably should. So
I'm pretty sure the lens of this.
I would bet a lot of money that it's cited there. Okay, any questions? Okay, so let's I want to talk about. So this talks about elasticity. I want to talk about something else now called the length function and boundary function. So let me kind of start this off. This is kind of both of these functions have behavior that's very much like a logarithm in a certain sense. The factorization analog of a logarithm. So definition. Well, 3.1. Let R be an atomic domain. You can extend this beyond what I'm going to do, but this will be fine for our purposes now. and star r minus 0. So just take your atomic length, well, 0 our star is going to be a function let's say we'll call phi. The non-zero elements are the natural numbers is called a length function. Yeah. Number one. Be of y. And two. Phi of x is 0 if and only if x is in the unit star. So
Can you think of this as a law function, or does it just behave like?
what's it?
Can you think of it as a law function, or is it just?
It behaves like one. This is like more primitive. Let me
Right,
give
right,
you,
it's not.
let me give you kind of a. And of course, one of the big things in this is that the function has to be well defined. Right, I mean, it has to be a function. Which for a lot of, so when I think of length function, I mean, here's what's gonna pop to my mind. Like, the length of the function is the number of irreducible factors, right? But of course, this may not be, well defined. If you have some element that has irreducible factorization, say 1,3 and another 1,7, then, you know, it doesn't make sense. But right here, this is just what we call a length function. Let me give you a proposition here. R is an HFD if and only if it emits a length function with a couple of properties. If, you know, only if R admits a length function such that the image, well, such that the image of phi is all the natural numbers and phi of x equals 1 if and only if x is irreducible. So, and the length function, if you have an HFD, the length function, I think is exactly what you think it is. If A is with each pi I irreducible in R, then, and this includes 0 in the sense that we'll say that phi of the unit, includes units in the sense that, phi of A is zero if and only if A is a unit. Notice this is multiplicative and it's well defined because of the HFT, and that's essentially what you need right here. Now, there is a ripoff of length function that you can define over the whole quotient field. Definition, let's let R and HFT with quotient field K. We define a function on the entire quotient field, well, the non-zero elements, I should say. We define function. We define boundary function partial R, K and Z, via the following. Okay, taking on with the quotient field, I can express this as because K is the quotient field of R as a fraction of two things in R. With each, so let me make a little notes here as I go along. Do that because it's a quotient field. Now, since this is an HFD, well, since it actually is atomic. 1, 2, R, N over where pi I omega J are irreducibles. N minus. So what you do is you take alpha, write it as a fraction, and that's a fraction of two non-zero things because I said that this is defined on non-zero elements of K. Factor top, factor bottom, and you get that. So this is the boundary function. Now, what's the first thing that this definition probably screams to you? I mean, this thing's potentially got all kinds of problems, doesn't it? Right? Because first of all, there's no way I'm believing that this representation is unique. So that's problem one. And even if it was, there's many, many ways potentially to factor both R and S, right? So the first thing is proposition. R, A star, and Z is well defined. And boundary R restricted to R is a length function. Let's go through why this is true. Well, let's suppose that. Uh, well, then, let's suppose, let's write out this way. Suppose R over S, so it doesn't matter, it's R anyway. Suppose this pi one, N over M. Suppose also that this is pi one prime, pi S prime. So suppose I have some fraction and I can represent where all these animals are. Well, this means that and as R is HFD, means that M plus P is equal to M S. Therefore, of no sleep, N minus M is S minus T. So this is what you get when you apply the boundary here. This is what you get when you apply the boundary here. And so it's well, and this depends heavily on HFD. Oh, and the restriction being a length function, well, all you're doing is your special case, S is a unit, right? It's pretty easy to see that this is multiplicative. I should say, let me have fun. Let me put this as well. Also note you have boundary alpha beta. Let's just write alpha and beta. I'll write them separately as quotients of irreducibles. Let's say, well, this is clearly N plus S minus M plus T. Right, and this is N minus M plus S minus T, which is boundary alpha plus boundary beta. Also note if U is in unit star, then boundary U zero. Right? I mean, I already know it's well defined, just take R and S to be the same irreducible if you like, and you get 1 minus 1, which is 0. Right. Is everybody okay with that so far? And once we have this property here, it's pretty easy to see that its restriction down to R is in fact a limit. Okay, any questions on that? There's one more thing that I always like to ask myself this. The first sentence bothers me, right? Because I hate too much restriction, right? Let R be an HFD with quotient field K. The boundary function is defined on, so the boundary function is actually defined on the non-zero elements of some field, right? Can somebody give me an example of a field that's not the quotient field of an HFD? Every ring of algebraic integers is quotient field of an HFD. See if I can see how. So here's what you do. If R is okay, let me, okay, I didn't think it was a straight example. I don't get, what did you, what was your comment?
I said any field is an HFDs.
Right. So, yeah, so, right, you can certainly do that, right? But then the boundary function is really stupid, right? It's always 0, right? So, let me rephrase, to be more careful. How many fields can you think of that are not the quotient field of a proper HFD? If R is a ring of algebraic integers, and P and R is non-zero, it's prime ideal. There you go. R localized to P, in fact, is U at D. Right, and they share the same quotient field K. So for example, in fact, the only fields that I am really sure of that are not quotient field proper HFD are the finite fields. Right, because they're only subrange fields themselves, right? I'm pretty sure. I'm gonna think about this. If I have to think about too much, I might give it to you. But I think probably you can do real numbers as well, right? But there's gonna be some maximum choice in there for sure. All right. So this condition, I think, is actually more non-restrictive than you might think when I first read it. It's like, oh, okay, Jim's only looking at 2 or 3 fields. Actually, it's pretty much anything I think you can think of. It's not a finite field. It's going to, and I'll see if I can think of counters. But for example, you might could, I would look at something like a valuation domain that has no height 1 prime ideal, and whose maximum ideal is the union of all probable prime ideal properly contained in it. But that takes some building, right? So anyway, yeah, I'll think about that. But anyway, if you guess a field, it's probably, and it's not, and it's infinite, then it's probably gonna have this property. Okay, any questions on that? So let me remind you of a couple of things here. So here's one useful thing about boundary map. Other than helping me write a few papers. Let me recall some facts for you that we've had in this class. The first fact is recall what it means to be almost integral. What are the ring quotient okay? And suppose that we say omega and k integral is one integral if omega is the root of a tonic f of x. Yeah, X. And almost integral if there exists a non-zero R such that R omega n is an R. Now, here's kind of the first sort of hint that the boundary might be useful, I think. And of course, we also know that any interval is almost integral. Here is a theorem. This is kind of a neat theorem. If is an HFD, okay, and alpha is almost integral over R. Then boundary of alpha must be greater than or equal to 0. So loosely speaking, very loosely speaking, if you have an element of the quotient field and it happens to be almost integral over R, that means that the number of factors in the numerator has to be at least as much as the number of factors in the denominator. This is kind of a neat thing because this means, because notice, if you take something with a negative boundary, you multiply it by itself, this boundary is getting more and more negative, you sort of get more and more factors in the denominator. Here we're saying if you're almost integral, the number of factors in the numerator have to always at least tie what you got in the denominator, if not beat it. Proof. As alpha is almost integral, there exists non-zero R and R with R alpha n in R for all n. All right. So this means boundary R alpha n alpha. Right, because the boundary of anything in R has to be greater than or equal to 0, right? Because you can think of an element in R as having a 1 in the denominator. So it's number of factors in the top minus 0. Everybody okay with that? The boundary is multiplicative. This must be greater than zero for all n. Finally. Because of the multiplicative like. So if boundary alpha is strictly less than zero, then there exists n natural numbers such that boundary r plus n boundary r alpha is less than zero, which is a contradiction. All you have to do is take n to exceed boundary r, and you've got it. Therefore, boundary r of my integral of homogeneous. And we'll discuss that further next time. Any questions? All right. Well, you all have a good one, and we'll see you on Thursday.